I haven't read it, but I'm wondering if some of you have. This is the second to the last problem on homework, chapter 5. Is it identical to what you see here, or is it reworded? Is it different?
I think mine's the same.
Okay. Okay, well, let's take a look. So last week, Robert and Jennifer added impurities to silicon to evaluate changes in its properties as a semiconductor. Well, whatever. I guess silicon, it is indeed used as a semiconductor, and it has to be very pure or it doesn't work as well. So they were testing adding these different elements, I guess. You can see how Robert and Jennifer use the elements indium in group 3A and tellurium in group 6A to try to make new computer chips and learn some of the properties of indium and tellurium. As part of a new research project, they were assigned to investigate indium and tellurium, the symbols IN and TE. So let's take a look at the questions. What is the atomic number of TE? Well, everybody knows. You don't memorize them, you look at the periodic table. I don't even know if it's a transition element. I think it must be.
Me too.
It is? Okay. And what is the atomic mass? Is that the question? Atomic number, yes. Huh?
Just the atomic number.
Okay, so it wants the atomic number 52, as you said. Okay, and what is indium? Might as well, since I'm here, 49. Okay. So 52 is what you write, unless you have indium, which would have to be 49. How many electrons are in an atom of tellurium? We are still considering neutral atoms, so the same number of protons, 52. On part C, use the sublevel blocks of the periodic table to write the electron configuration of an atom of tellurium. So looking at that periodic table, tellurium is in block P, right? And period 5, so it will have electrons on 5p, and the position on the p block is 1, 2, 3, 4, so it will have 4 electrons on that 5p subshell. I think we've done that before, so I'm going to skip it so that we can move forward. And in one of them, you need to write the entire configuration. On the other one, you need to use the abbreviated. You also know how to do that. Now, this is going back to the trends that we looked at, which were somewhat intuitive for some of the trends and counterintuitive for some others. So an atom of selenium, so we need to find where selenium is right above tellurium, still in group 16, atomic mass, atomic number 34 from what I can see. And the question is the atomic size larger or smaller? Well, remember once again, the trend can be counterintuitive to some extent. But if I draw a quick periodic table here, we're looking at atomic radii. And that actually increases as you go down the periodic table. Okay? That's the trend we're looking at right now. We have selenium here, tellurium down there. So selenium is going to be smaller than tellurium just by its position on the periodic table. So has a smaller atomic size. That's the intuitive part, because as you increase the atomic number, you increase the radii. What is counterintuitive, but we went over the explanation last Tuesday, is the trend in this direction. And in that direction, the way I put the arrow is for decreases. This is increases. So radii gets larger as you move down the periodic table, but it gets smaller as you move to the right on the periodic table. And that's because of the attraction of the protons for the electrons. Okay. Now, we did not talk about ionization energy trends, but there's another figure in your chapter that tells you those trends. And how easily an atom ionizes is also something that you can predict by looking at the periodic table. Let me request the answer so that, oh, never mind. I guess it doesn't give me the feedback. But just look at that table, which is going to be very similar to the one dealing with atomic radii. And you just interpret, the trend. The same logic. That's why I'm skipping that topic.
Can we go over 17?
Problem 17, I'll go back to that. Okay. Let me just take a quick look at 19. Okay. So once again, you look at the trend on this last question. Largest atomic size in period 6. So we go to the period. And because the trend is from left to right increases, you just go to the end and indicate that one as the largest. And the other questions in this same problem are the same type of questions. So let's go back to 17. Okay, so this has to do with the valence electron configuration for each of the following. Okay. Express your answer in order. Yeah, this is an interesting wording.
That's what I was confused about, is how to enter it.
Yeah. Let me try to write the valence electron configuration for each of the following.
Because I wasn't trying to enter it.
Arrow before you move on to the next thing. It was a pain. I got it all wrong.
Did you?
But did you guys figure it out? Because I love some.
The answer is right. It's how you input it into the system.
Okay, so I mean, I always welcome input from your own approaches to these problems. It gets pretty tiring for me to be repeating the same thing over and over to you guys. But I mean, tiring for you, I imagine. But you guys sometimes have different approaches to the same question and how to solve it, so I love to hear them. Let me see if I'm understanding this right. So the electron configuration of the valence shell, right? Only the outermost, not the internal ones. And for that, they give you group 2A. So if we go to group 2A, so all right here, we know just from the get-go that that's going to have a tendency to lose 2 electrons, right? Group 1 loses 1 electron, becomes +1. Group 2 loses 2 electrons, becomes +2. Now, what does that mean? That means that it's actually having 2 extra electrons there on that level that rather be lost than fill the rest of the circle. So let's take a look at any element in that particular period. And I'll go from starting with group 2. One, 2 circles, okay. So in the outermost shell of beryllium, you're going to have 2 electrons. On the outermost shell of the next one below, magnesium, so this is beryllium, this is magnesium, you're going to have 2 electrons. It doesn't matter what is inside. We're only looking at the inside. In the next one, below magnesium, calcium, 1, 2, 3, 1, 2 electrons. And if we look at the levels, so this is the second period, the third period, and 1, 2, 3, I guess I'm missing one. 1, 2, 3, 1, 2, 3, 4. And this is the fourth period. So all of them seem to share the fact that they have 2 electrons on the S subshell. But we cannot write a number here because they're looking for all of them combined. Does that make sense? So that's why they're using an N. The N means any number between 1 and 8. So any element in there, the first digit can be 1 through 8, but the S and the number here has to be S2. Now, what is it that the system expects? The entire thing just
Put an arrow
NS.
between the numbers every time.
Okay. Well, this is my interpretation, so let's see. And write the valence electron configuration. My guess would be to write it just like this. Just like that. Because they're not expecting the internal ones. Would imply having to write N S2P6 for, right. So that, yeah. Now let's look at group 14.
So 14 would be NS2
14.
and P2.
Right. You got it. So group 14 is the second block on the P block, the second group on the P block. So it will have 2 electrons. So that's exactly right. And S2 and P2. Okay? You got it. Now, I don't think that will work for D because remember in D we actually lower the number by 1. So I hope that
The question doesn't ask any for
any D or F block. Okay. Is everybody sort of following what we're talking about? I feel like I'm skipping steps, but I think that's the bottom line. Thank you for asking for that.
Yeah, so I was like, yeah, confused how to enter it. Okay.
Yeah, it stumbled me. When I first read it, I was a little not sure what they wanted. Okay. Now, if you've done the quiz and you have questions about the quiz, please do let me know. Otherwise, I'm not going to open it and I'm going to let you work on that. Remember, you have 2 attempts for the quiz. My suggestion is that you take the quiz. Anything that you get wrong, you review, and then you take the second attempt. What?
Oh, I was like, what quiz are you talking about?
Chapter 5, still.
That's done.
Okay.
That's done.
Now we have to switch gears. And I'm going to turn off the screen, but I do need my PowerPoint here to guide me. Because we're going to switch to chapter 6 finally. Now, chapter 6 should come somewhat, it should become somewhat in a second nature, to put it in one way, because you're going to be applying what you learned in the previous 2 chapters. This is just not working. What do I mean by that? Well, we're going to combine the understanding of how elements on the periodic table, as they come from the periodic table, are unstable, and they are always seeking stability. They're always trying to find a way of being a little bit more, less reactive, if you will. And for that, we're going to have two possible scenarios here. The first one you already sort of know. That is, an element has a tendency to lose electrons if it has few electrons in its valence shell. An element has a tendency to gain electrons if it has many electrons in its valence shell. Now, what do I mean by few and many? Well, we're going to talk about something called the octet rule. And the word octet comes from the word 8. So octet means 8. When you look at the different elements in the periodic table, I'm going to start with the old one that we've been using, sodium. So sodium has one shell, two shells, I believe. No, three shells. And this is going to be sodium. And chlorine is going to have one shell, two shells, three shells. We're minimizing, we're simplifying now the SPD subshells. We're not going to be talking about their shapes. We're just going to be talking about the outermost shell having a tendency to complete an octet, to have 8 electrons. That's what makes an element stable. So sodium in its valence shell has 1 electron. Chlorine in its valence shell has 7 electrons. So 1 electron, 7 electrons in the valence shell. The octet rule states that all elements want to have 8 electrons in their valence shell. Now, here's the problem. For chlorine, it looks easy. It has 7 electrons, right? So to complete 8, all chlorine has to do is find 1 electron somewhere. It doesn't matter where it comes from. Just picks up 1 electron. That 1 electron becomes a member of that valence shell of chlorine. And now chlorine has an octet. So when that happens, now we have not 7 electrons, but 8 electrons. And chlorine has a charge of -1 because we added 1 more extra electron to the same number of protons that chlorine had before. So 17 protons, 17 electrons, no charge. We add 1 electron, 18 electrons, 17 protons, charge of -1. So that's easy to sort of explain. But what happens to sodium? Well, sodium would have to pick up 7 electrons to complete 8 because there's room for 7 more electrons in its outermost shell, in the valence shell. That's actually energetically very, very difficult. Can it happen? Can it be done in the lab? Yes. But it doesn't happen unless you force them in the lab. In nature, it doesn't happen. So what is it that happens in nature? That electron leaves the sodium atom. So if this electron leaves, this shell now is still there, but it's empty. So the valence shell becomes the next internal shell, this one, which now we have to write that it has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now I'm going to erase it, but please keep in mind that it's not gone. It's still there. It's just empty. But now the outermost shell with electrons for sodium, when it loses 1 electron, and it becomes +1, has 8 electrons. And that's how it happens to elements in group 1. It doesn't matter if it's sodium, it can be potassium, it can be cesium, rubidium. Any member of group 1 is going to have the same behavior as sodium. Same thing for members of group 17. Just like chlorine, fluorine, bromine, iodine, those are going to have the same tendency to pick up one electron and become negatively charged with a -1 charge. Now, what happens with other elements? Well, we're still going to keep talking about losing or gaining electrons. We're going to move to group 2 or 2A. In group 2 or 2A, you have an outermost shell with 2 electrons, as we learned in chapter 5. 1, 2 electrons. There's room for 6 more. Picking up 6 is going to be almost impossible. A little bit less impossible than group 1, but still pretty unlikely. So what happens? Elements in group 2 tend to lose 2 electrons. And that, for instance, would be magnesium. So magnesium loses 2 electrons and becomes charged 2+. You do the arithmetic. Magnesium atomic number 12, so it starts with 12 protons, 12 electrons. Now it has only 10 electrons, so it has a charge of +2. Any member of group 2 is going to behave the same way. So you can make the same prediction for calcium, for strontium, for barium. And now we move to group, we're going to skip for this next chapter elements in the transition, in the D block. We're going to skip all the way to the P block. Now, using the new system of numbering, the first elements on the P block are in group 13. Okay? Group 13 is the first group in the periodic table. So this is 13 right here. These elements are the next ones that we're going to talk about in regards to the octet rule. Keep in mind, by losing 2 electrons, this guy now has an octet, which is what they are attempting to do. But what happens then in group 13? Well, in group 13, oops, wrong color, anyway. There are 3 electrons in that outermost shell, P3. Any member of group 13 is still trying to get 8 electrons in that valence shell. Well, I hope you see that we're still away from 8 by more than close to 8. Does that make sense? I mean, if we lose 3 electrons, we're going to get the next level inward with an octet. If we gain 5 electrons, we're going to get this level with an octet. Gaining 5 is more difficult than losing 3. To this point, we're still safe saying that. And that's what happens. Elements in group 13 have a tendency to lose 3 electrons. And the example that I can give you is aluminum, which when it loses 3 electrons, it becomes charged with a positive 3 charge, 3+. So now comes group 14. So group 14 has 4 electrons in its outermost shell. It can lose 4 or it can gain 4. It's right smack in the middle. What does it do? We're going to take a break from gaining or losing electrons, and we're going to skip it for later. We're just going to say that for just a few minutes. So members of group 14, yes, they could gain 4 electrons. Yes, they could lose 4 electrons to complete an octet. But it's going to be slightly different from what we've been talking about. So we're going to skip that. Now let's move on to group 15. So let's put group 15 here. An example would be nitrogen. Nitrogen number 7 on the periodic table has 2 electrons in the innermost, they don't count, and then it has 5 more, 1, 2, 3, 4, 5 on the valence shell. So that would be nitrogen. 1, 2, 3, 4, 5. It can do two things: lose 5 electrons, which I hope you see is less likely, or gain 3 electrons, which is more likely. So if it picks up 3 electrons, 1, 2, 3, it now has an octet. So we're picking up 3 electrons, 3 negatives, which makes this nitrogen atom have a charge of 3 minus, negative 3. So things become a little bit more complicated when we talk about atoms that gain electrons, because the charge becomes negative instead of these pluses that we were seeing before. But once you understand that, it's predictable, and it's fairly easy to predict. So any member of group 15 to complete 8, it has 5, it picks up 3, has a charge of negative 3. That includes phosphorus. Group 18, same idea. Group 18 has 1 more electron than nitrogen had, so it has 6 electrons. A member of group 18 would be oxygen. 1, 2, 3, 4, 5, 6, 7, 8. 8 is the atomic number of oxygen. It picks up 2, so it carries a charge of negative 2 when you add 2 negatively charged electrons. And that completes an octet. And we already looked at 17. 18 we don't look at because those guys don't mingle with any other element. They don't lose electrons, they don't gain electrons, they just stay put. Now, very briefly, because we need a little bit more time to understand what's going to go on with members of group 14 and sometimes members of group 15 or even 16. So just very briefly, let's do the electron orbits of carbon. So here is the core, first shell, second shell. Carbon, an incredibly important atom in biological systems. We all have lots and lots of carbon in our cells. Every item of food that we eat contains carbon, whether it's protein, carbohydrates, or fats, all of them have carbon. So carbon is fundamental for life. It happens to be in group 14. It has an atomic number of 6, so that means it has 6 electrons. 1, 2 in the first one, and then 1, 2, 3, 4 in the second one. That means it can lose 4 electrons or it can gain 4 electrons to complete an octet. Well, it doesn't do either of those two things. Now, I'm going to draw carbon in a slightly new way. One thing that we haven't done so far in this semester, but it's extremely useful, you guys. I hope you really spend time understanding what I'm going to show you right now. This is going to be called the Lewis, that's just a last name, dot symbol or structure. And what we're going to do is we're going to write the symbol of the atom, and then we're going to place electrons around the symbol. Now, it's not that straightforward because I'm going to show you that I'm going to place an electron here, one there, and one there. Remember, carbon has 4 electrons in its outermost shell, in the valence shell. I'm showing them to you here, surrounding the symbol of carbon. Now, I could have written them like this, or I could have written them like this, so on and so forth. Why did I choose these? Well, that's the way Lewis determined was the best way to do it. And I'll show you very quickly why. If I want to do the same for sodium, I just put one dot. If I want to do the same for magnesium, I put two dots, but I'm not going to put them next to each other. I'm going to go around. There are 4 locations for these electron dots. 4 locations, top, bottom, right, and left. So the second dot of magnesium, I'm going to put it to the right. It doesn't really matter if I put it to the right or to the left, but be consistent. Develop your own system. And I like to go top first, then I go clockwise, and I start adding electrons. So if I do that for aluminum, which has 3 electrons, it's going to go 1, 2, 3. Then we have carbon. Then we have nitrogen. So nitrogen has 1, 2, 3, 4. Guess what? Now we need to start pairing them. So I go back to the beginning where I started on the top, and I put the 5th one right there. That's a pair of electrons. It's going to be super important later. If I count dots, I have 1, 2, 3, 4, 5. 5 electrons. Next one, oxygen. 1, 2, 3, 4, 5, 6. I'm pairing them now, still going clockwise. Chlorine, 1, 2, 3, 4, 5, 6, 7. We don't touch group 18. So these electron dot symbols are very useful because I'm going to try to explain to you what happens in the case of carbon. So in the case of carbon, carbon does not give up its electrons, doesn't pick up electrons from anyone. It becomes to an arrangement, an agreement, if you will, with other atoms to share electrons. So we're going to use this word to describe what happens to the electrons on the valence shell of carbon. Now, I'm going to make it very easy, not to you, but for me, to show you one of the best examples of how carbon can share electrons with other atoms. And for that, I'm going to add one more element here that we haven't talked about. Now, hydrogen is a little bit different from everything else that we have said because hydrogen doesn't obey the octet rule. I mentioned to you much earlier, probably 2-3 weeks ago, that hydrogen likes to complete a duet. So 2 electrons is all hydrogen ones in the outermost shell. Hydrogen, when you look at the periodic table, has only 1 electron. Atomic number 1, 1 proton, 1 electron, right? So we have hydrogen with 1 electron. Carbon has 4. Carbon is always looking for 4 electrons to share. So this is what we're going to do. We're going to bring hydrogen here in the old-fashioned way that we've been doing, so hydrogen here. And this 1 electron that hydrogen has is going to come very close. It's in fact going to overlap with the atom of carbon. So if I bring this closer and closer, eventually the orbit of hydrogen that has the 1 electron overlaps the orbit of carbon with those 4 electrons. One of those 4 electrons is going to like to stay around that area where the 1 electron of hydrogen is. That overlapping is what we call sharing. So you have 1 electron from carbon pairing with 1 electron from hydrogen. But that doesn't help carbon very much, right? That's only 1 hydrogen, only 1 electron. If we count the 1 electron that hydrogen is contributing to this relationship, Now carbon has 5 electrons, right? Or at least it feels like it has 5. It needs 3 more. So quite simply, this is what happens. 3 more hydrogens come to the association, to the relationship, to the partnership. One here, and one here, just to make it show clear. Now, rather than making this very cumbersome and making this drawing too complicated, let me draw it over here using Lewis dot structure or Lewis dot symbols. So I'm going to put carbon, 4 electrons, 1, 2, 3, 4. That's my carbon. I'm going to bring hydrogen, and just for clarity's sake, I'm going to draw the electron dots of hydrogen as little x's. They're still dots, but so I'm going to put 1 here, right there, 1 here, right there, 1 right there, and 1 final one right here. Each hydrogen brought 1 electron to this partnership. Carbon is happy to share those 4 electrons one at a time with each of those 4 hydrogen atoms. Now carbon, if you count, has 1, 2, 3, 4, 5, 6, 7, 8, or at least it feels like it has 8. It's sharing. Hydrogen has 2, it has a duet. Hydrogen has 2, it has a duet. Hydrogen is super happy. This is actually a molecule of a compound that when we write the formula, and we're going to go that far later in this chapter, we write something like this, CH4. Now CH4 actually has a name. You may have heard it or you may have never heard of that, but it's called methane. And it happens to be a gas at room temperature. Sometimes it can even be used for burning, for heating up homes. You probably have heard of propane or propane. Propane is really similar to methane, but instead of having 1 carbon, it has 3 carbons. So very quickly, let me just show you where we're heading. If I want to draw the structure of propane, I have 1 carbon, 2 carbons, 3 carbons. That's what propane has. Each of these carbons is going to share 1 electron with each other. So 1, 2, 3, 4. 1, 2, 3, 4. And then maybe I'll do 1, 2, 3, 4. These 2 right here are going to be shared. So keep that in mind. These 2 right here are going to be shared. Keep that in mind. I'm going to tell you that also later this chapter and next chapter, any time that you have a pair of electrons being shared between 2 atoms, instead of writing the 2 dots, we write a dash. So a dash represents a pair of shared electrons. Anytime you see a dash in any formula, in any symbol, in any compound cartoon, you know that there's a pair of electrons there. So by the same token, these 2 electrons right here, I'm going to draw them with a dash. Now if we count, this is going to be propane. If we count electrons, this carbon has 1, 2, 3, 4, 5, right? It's still needing 3. This carbon right here has 1, 2, 3, 4, 5, 6. That one is closer to 8. This carbon has 1, 2, 3, 4, 5. So how do we complete the structure for propane? For every dot that doesn't have a partner yet, we're going to add a hydrogen. As straightforward as that. So 1 hydrogen here, 1 hydrogen there, 1 hydrogen there, each hydrogen with a little x. 1 hydrogen here, 1 hydrogen there, 1 hydrogen here, 1 hydrogen there, and 1 hydrogen there. And now we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and importantly, 2 for that hydrogen, 2 for that hydrogen, a duet for every hydrogen. If we replace all of those pairs of electrons because they're being shared with dashes, we have what you probably have seen in books before or in biology, a molecule with every bond shown, and this happens to be propane. Now I took a long, I guess, tangent here or detour because we need to go back to the elements that lose or gain electrons, not the ones that share. The ones that share come next. But right now I just wanted to show you that that's what happens to elements like carbon. Okay? Can other elements share electrons instead of losing or gaining? Yes. Oxygen can gains 2 electrons, or it can share 2 electrons. Nitrogen can gain 3 electrons or share 3 electrons. It's going to depend on the partnership that is formed between different elements. But let's go back to when you lose or gain electrons. Any questions? So this is now taking us deep into chapter 6, believe it or not. But chapter 6 also is going to help you make predictions using the periodic table so that you can not only write the symbols of different compounds, if you will, but also predict their names. And then also from the names, predict the formulas of those compounds. We're going to spend the next few minutes talking about a group of compounds known as ionic compounds. Brand new topic in chapter 6. We have seen several ionic compounds already, at least one. So an ionic compound forms when you have a metal giving up electrons to a non-metal. So all ionic compounds have a metal and a non-metal, at least. They can be more complicated than that, but at the very least, you're going to have a metal and a non-metal. Now let's form some ionic compounds, and we're going to predict their actual formula. So let's start with the one that we already know, sodium. Sodium loses 1 electron, so it becomes charge +1. And I'm going to put the charges on the top. Sometimes I write +1, sometimes I write 1+. It's the same thing. The position of the plus sign doesn't matter. Okay, bear with me. So we have sodium there. Lost an electron, charge of +1. Chlorine here. Gain an electron, charge of -1. When we combine these two, when we add those two together, we get an ionic compound with a formula. That ionic compound is going to be written as follows. Na, the metal first, followed by the symbol of the non-metal, and basically attached to each other, I mean next to each other, like 2 letters in a word that are contiguous. So we write the 2 symbols contiguously, no spaces, one next to each other. Now, I don't want to complicate the picture right now yet, but I'm going to mention something to you a little bit earlier that you're going to have to remember that that's just always the case and it's always too simplifying. Let's make the prediction of what would happen if we combine sodium with a charge of +1, but this time we're going to add a member of group, let's say 16. So if I add oxygen, and that oxygen happens to have gained 2 electrons, that is going to have a charge of 2 minus, -2. Right? Oxygen gains 2 electrons, -2. Can we predict the formula of that partnership? And the answer is yes. But here it becomes a little tricky. We still write the metal first. Na comes first. We'll still write the second element, the nonmetal, as one contiguous word. But unfortunately, we're not done, because the charges of these two ions need to cancel each other out. In other words, we have to have an ionic compound with a net charge of 0. It cannot have a charge. It has to be 0. Here comes the straightforward way of figuring it out. You simply look at the numbers on the top, and you write them in the new formula that you're predicting as a subscript, but crisscrossing. So you're going to take this 2 that is on top of the oxygen here, and you're going to put it as a subscript in front of the Na. This is how you do it easy. The explanation comes next, but that's how you do it easy. You take these 2, you ignore the negative sign, because this is just telling us how many sodiums that are going to be there, and you put it as a subscript of the symbol sodium. This +1, we do the same thing. Crisscross, put it at the bottom to the right of the oxygen. And that's the formula for the compound that forms when those 2 come together. However, we didn't write a 1 here and a 1 there, right? Well, that's actually by convention. To facilitate things, anytime you have a symbol, an element, in which there's only 1 atom of that element in a formula, you don't write the 1. So we don't write this 1. And that becomes the formula of Na2O. Let's make another prediction. One using members of group 2 and members of group 17. So magnesium is in group 2. So it's going to have a charge of +2, right? It should become, or start becoming, almost second nature, how you predict the charges. If we combine that with an element from group 17, let's say fluorine, fluorine is going to have a charge of -1, right? Group 17 gains 1 electron, becomes negatively charged with 1 minus. What's the formula for that partnership? Well, we do the same thing. We take the numbers that we have for the charges on top of the symbols, we crisscross them and put them as subscripts in the new formula. Let's just write the symbols first. Mg comes first because it's the metal, fluorine second. Now for the subscripts. This 2 is going to become the subscript of fluorine, so we're going to put it right there. This 1, without the negative sign, is going to become the subscript of magnesium, so we put it right there. But we said earlier that ones we don't write, so I'm going to erase it. And that right there is the formula for the partnership between magnesium and fluorine. I'll give you a difficult one for you to figure out, and I mean that because I think you will be able to do it. And for this one, we're going to take a member of group 13, aluminum. Group 13 loses 3 electrons, so charge of +3. We're going to combine that with oxygen, which we had here before, which has a charge of -2. please go ahead and predict the formula, and then we'll check it together. Okay. Everybody ready? Metal first, non-metal second, crisscross. These three comes down here. These two comes down in front of aluminum. And if you predicted that, that's the right formula for that compound. Now, as you can imagine, we have actually names for these compounds. So I have mentioned the name for this one before. Let me write it now again because we're going to see a pattern. So we have sodium chloride. So how did we name that? We grabbed the name of the first element. We took the second element, and instead of calling it chlorine, we changed the suffix, the ending, sorry, to IDE, so it's chloride instead of chlorine. And that's all we did. So by the same token, this is going to be called sodium oxide. So instead of oxygen, it's oxide. That's not that intuitive, but it's nevertheless the way it is named. One quick second here. And then let's predict the name of the third one. So we have the name of the first element, magnesium. The first element, the metal, never gets renamed. It's just the name that appears in the periodic table. Magnesium. And then fluorine becomes fluoride. Wow, we're making great progress here because now we can name somewhat simple elements. This one, it doesn't matter that you see 2s and 3s there. We simply call it aluminum oxide. Now, if we can do that, can we do the reverse? Can I give you the name of a compound and you write the formula? In this case, we were learning the process, so I gave you the ions. Now I'm going to give you this formula, or I'm going to give you this name, and you're going to have to tell me the ions, or you're going to have to tell me the symbols, the formula. So let's start with something somewhat simple. I'm going to ask you to please predict, the formula for potassium bromide. And then do the same prediction for potassium sulfide. So we're going to work in reverse. I'll give you a minute to see if you can make the prediction. Let me put a table here. To help us a little bit. So how do we write the chemical formula from the name? Well, working in reverse, we're going to always write the symbol for the metal first. So if we look up the periodic table, potassium is K. We look at the periodic table, and bromide sounds like bromine. I mean, at least to me, but you know, I've done this before. I hope it sounds to you also like bromine. So bromide, bromine. That has, that's in group 17, and it has a symbol of Br. So we'll just write that. Now here comes the little tricky part. So now we have the two symbols, but how do we know the charges so that we know the subscripts? Well, we look at the periodic table, and this guy has a charge of 1 plus. This guy has a charge of 1 minus. So I'm using this as a guide to crisscross. If I crisscross, I have 1 and 1, but I don't write ones, so I erase them. And because this was just my guide, I'm going to erase it. That was just for me to know the subscripts. And KBr is potassium bromide. So what about potassium sulfide? Well, we do the same. We put the symbol for the first element, the metal. Sulfide sounds like sulfur, I hope. If it doesn't sound like sulfur to you, I'm telling you it is sulfur. So S. Potassium hasn't changed, it's still in group 1, 1 plus. Sulfur is in group 16. So it means it's going to gain 2 electrons, so it's going to be 2 minus, right? Now we crisscross. This 2 comes down here without the negative sign. This 1 comes down here without the positive sign. So K2S1 is the formula. We don't write ones. I'm going to erase it. My guide is gone because I already used it. And K2S is the same thing as potassium sulfide. Now, in your textbook on chapter 6, there's a little table giving you the ionic charges of the elements that are involved in the first few ionic compounds that we're going to be dealing with. So you can combine, and you can practice combining any of these positive ones with any of these negatives. And what you're going to call them is very straightforward. Barium sulfide, barium iodide, potassium oxide, so on and so forth. Now, some of them are a little bit trickier than others to write. So for instance, let me ask you, okay, what would be the formula for aluminum phosphide? So aluminum phosphide so according to this little table, aluminum has a charge of 3 plus. Same table has phosphide with a charge of P of 3 minus. So, okay, so this is an interesting one because we have aluminum with 3 plus and phosphide with 3 minus. So what's the formula? Okay, we crisscross. The 3 comes down here. The 3 comes down here. I'm going to erase my guide now. And I'm going to be tempted to say that's the formula of aluminum phosphide, Al3P3. But here comes one complication. And it's not a complication, it's actually a simplification. Whenever possible, the subscripts that you write are going to be reduced to the most simple explanation or expression that you can come up with. In other words, if you remember the word or the term common denominator, the common denominator of these two is 3. So if I divide both numbers by 3, I get 1. So a better formula, not that this is awfully wrong, but a better one would be AlP3. P1, I mean AlP, sorry. I'm getting confused here. Now, if I put the charges back, 3 plus and 3 minus, and I'm saying I have one of these and one of those two do cancel each other out. They add up to 0. So what have we learned right here? Well, that in fact the subscripts do tell you something about the number of partners in the formula. So in this case, aluminum phosphide has one aluminum for every phosphide, one of these for every one of those. Potassium bromide has one potassium for every one bromine or bromide. But this one is interesting. This one looks like this: one potassium, two potassiums, only one sulfur. Why is that? Well, because this guy has a charge of 2 minus. Each of these have a charge of plus 1. So you actually need 2 of these guys, each of them giving 1 electron, to sulfur, which likes to pick up 2 electrons. So potassium cannot give 2 electrons alone. So you need 2 potassiums doing the giving up, the lending the electrons. So that's essentially what those tell you. Now, it gets a little bit more complicated when a couple of things arise. So sometimes you have more elements in one ion. Let me move on to the next section. And of course, I'm not going to be able to cover that completely right now. But let me give you a preview. And then we'll talk about some of the properties of these elements, of these compounds. Sometimes we have elements in an ionic compound that have more than one potential valence electron configuration. These are called oxidation states. So it was easy to predict elements in group 1 having a charge of plus 1, elements in group 2 having a charge of plus 2. But some metals in the transition part of the table, because nature, it is what it is, have more than one possible electron configuration in the valence shell. We're going to call those oxidation states. Chemists have come up with a way of describing that by using Roman numerals. So let's take a look at, let's just use copper to begin with. So copper exists in 2 different ionic forms. You can have copper plus 1, or you can have copper plus 2. In this table, they don't put the ones, they make it even simpler. But this is plus 1, plus 2, 2 plus, 1 plus. So it turns out that copper, a metal, can form 2 compounds with oxygen. So we can have copper with oxygen, or we can have copper with oxygen. But they're 2 different compounds. We're not done. These are not the formulas. If the copper in this top example is this copper, the charge, I'm going to put it right here, 1 plus, is interacting with the oxygen doesn't change, it's 2 minus. So 2 minus. What happens when we crisscross? We get Cu2O, right? You know how to do that now. In the second type of copper, the one with 2 plus, when we crisscross, we end up with C2O2, but we need to simplify it by the common denominator. So 2 divided by 2 is 1, 2 divided by 2 is 1. Once we don't write, the number 1 we don't write, so the formula for this second type of copper compound is CuO. So now we see that clearly this one indicates that this copper has an oxidation state of +1, and this copper has an oxidation of +2. How do we distinguish them by name? In the old system, and is no longer used, these used to be called cuprose, and these used to be called cupric or copric. Today, to make it easier for people like with accents like me, we use Roman numerals. So if the copper in the formula is using the charge +1, we're going to add a Roman numeral in front of the name of the element before we name the second element. So this guy right here, copper, is using the +1, so we're going to say 1 in parentheses with a Roman numeral, and then we add the rest, oxide. So we call this copper 1 oxide. That gets rid of the ambiguity. This one is using the 2+, so we call it copper, parentheses, Roman numeral 2, oxide. So now if I were to give you a problem in which I'll give you the name of a compound and I want you to write the formula, I hope you would be able to. This is now elevating, raising the bar and making things a little bit more difficult. So let's write the formula for chromium. Three oxide. So chromium, another transition metal, can exist as 2+ or 3+. I put a Roman numeral of 3, so I'm telling you the charge is going to be 3+. So what would be the formula that you predict for chromium oxide? Well, let's do it together. Symbol for the first one, Cr. Just look at it at the periodic table. The charge on that first one, 3+. Oxide is always 2-. Oxide, 2-. Now we crisscross. I'm going to do it right here in front of this one instead of writing it new. So this 3 becomes a 3 right there. This 2 becomes a 2 right there. There's no way of simplifying that. There's no common denominator. I erase the charges because they were just my guide. And Cr2O3 is a formula for chromium 3 oxide. Now remember, as I said earlier, that means that in this partnership, you have a chromium here, a chromium there, an oxygen here, an oxygen there, and an oxygen here, all mingling together. That's what this tells you. You have 3 oxygens, 1, 2, 3, for every 2 chromiums, 1, 2. And that combination gives you a net charge of 0. Now, next week, we'll talk about some other complications. Not terrible, but of compounds in which you have ions that's really tiny, a composite of 2 nonmetals.